Welcome back to the course in Nuclear Medicine Physics. Today, we're continuing our discussion on SPECT imaging. In this lecture, we'll look specifically at something known as quantitation. You want to know how much radioactive material there is at a particular region in the body. In order to do this, we can't just take raw data and reconstruct it. There's actually a number of corrections that we need to make first. For example, some of the radiation gets attenuated by bones and muscles, and this is different in different regions of the body. So in regions where there's a lot of attenuation occurring, or a lot of the radiation gets absorbed in your body, you're not going to measure as much radiation from the detector. But this is wrong because you know that there's radiation in that region. And it turns out there's ways to correct for this by taking, for example, a CT image. Once we know all the corrections to do, we can modify our data set and then use mathematical algorithms to reconstruct the radiation inside a patient.
All right, so we're gonna talk about in this second part lecture on SPECT imaging on quantitation aspects, quantification or quantitation aspects. So what is quantitation? What do we mean by that? All right, so there's really that word can be used in two senses: relative versus absolute. So relative quantitation is when you're kind of measuring activity in one location relative to the other location. So you want them in relation to each other to represent the correct counts. So you don't need the absolute counts, but you need the relative counts to be appropriate. So if you're looking at you're comparing the activity in a particular region of interest versus activity in some other region of interest, in some background, you're looking at activity or total activity and things like that. Absolute quantitation, there's a lot of increasing interest in this over the years, and PET has been leading on this front. And for a long time, people thought SPECT cannot do it, but SPECT definitely can do it, and it has moved in that direction. And we're talking about that today. Is where you're kind of measuring absolute numbers. So, for example, you could be measuring, you could be looking at an image, and for each pixel, it could be telling you, what is the absolute units, let's say in micro curies per milliliters or in kilobecquerels per milliliters. And these two, as we've talked about, are highly related. They're off by a factor of 37, for example. But that doesn't matter. The point is, kilobecquerels per milliliters, right? So can we do that? And there are some interesting applications for that, like especially SPECT is being used increasingly for doing dosimetry. We talked about this exciting area of theranostics and how when you're doing you're delivering therapy to a patient, radiopharmaceutical therapy, also known as radionuclide therapy or molecular radiotherapy, you're actually able to monitor and quantify how much dose you're giving, for example, to the organs at risk or to the tumors. And the way to do that often is with SPECT imaging, let's say in lutetium-177. And so having absolute numbers is going to be important because you want to know how much dose is exactly, how much radioactivity is there, and from that you can calculate dose given to the tumors and organs. Also for cancer applications, just like in PET, where we've been using this thing called the standard uptake value, SUV, and we're going to talk about that a lot more later in the context of PET. Which requires you to have these absolute units, which are then normalized to the injected activity and the weight of the patient and things like that. Well, guess what? SUV is also starting to happen in the world of SPECT, where SPECT would be used in that sense. So the question we're having here is exactly. So as you think about cancer more and more, so this area, relative perfusion imaging, for example, in the heart has been important. More and more people have wanted to get rid of artifacts in the images and to make relative perfusion more reliable. But even in the heart, there's been interest in absolute quantification, right? So, and that allows you to look at myocardial blood flow and coronary flow reserve and things like that. So in the heart, both are interesting. In cancer, as I was just saying about SUV, standard uptake value, you need absolute quantitation. So you take these numbers and you divide them by the injected dose, and weight of the patient and things like that, but you start with the absolute numbers. So in treatment response assessment, monitoring cancer, absolute quantitation has become more and more interesting and important. So PET has been doing that, and SPECT is getting there. Okay, so what are some of the issues with SPECT imaging? Okay, so one is the quantitative capabilities. The point is that this has been elusive. Okay, and these are the three things that have been changing, especially the first two, especially the first one. In fact, attenuation. Attenuation in SPECT has been a difficult problem. And so for the longest time, people would say SPECT is not quantitative because attenuation is not dealt with properly. Unlike PET, it turns out for PET, attenuation correction is more straightforward. You'll see later why that is. But in short, the reason is because you have dual photons. And so the probability of attenuation depends on the total path length going both ways to both detectors. Doesn't depend on where the source is from along the line of response. It just depends on the total intersection of the line of response with the body. It doesn't matter where on that line of response you came from. But in SPECT, that's not the case. You got single photon. For a projection, it really depends where you are on that line. What is the distance from you to the detector? But the point is, attenuation has been difficult, and people thought SPECT is not quantitative because you cannot deal with attenuation. But that is not true. It is now being dealt with quite nicely. So SPECT is increasingly recognized as quantitative, and above-mentioned issues have been systematically addressed. Attenuation, then comes scatter, and then then comes dealing with those resolution problems that we mentioned in the last lecture too. The fact that as you get away from the gamma camera, the resolution degrades, and how do you deal with that? So statistical iterative image reconstruction has really allowed SPECT to become quantitative. This is a very important take-home message. If next time somebody tells you SPECT is not quantitative, you may want to tell them maybe on this scanner and this particular implementation when no attenuation correction is being done, or some kind of a really old school attenuation correction is being done, maybe. But SPECT can be made quantitative. So let's see what that means. So again, just looking at these different things that could happen. So you could be having a perfectly fine event, on its way to detection, but then it's attenuated. And that can happen due to either photoelectric absorption or content scattering. We'll see that in a second. So it may not be, you may not make it all the way. Okay, and this is an example. So it was meant to be detected, but it wasn't. You could also have scattered photons. So this was, this event A itself too. If it's scattered, it's similar to here. A and B are kind of quite related actually. So A could undergo photoelectric absorption, so it would be terminated in a sense. Or it could be scattered, kind of like this event could be scattered and never be detected. So this is an example of a scattering that is never recorded. Okay, but you could have an example where this event was going to go this way, but it was scattered, and now it is detected. Okay, so this is a now scattering problem. You have detected an event because it was scattered, and what do you do with that? So it is possible because of scattering for you not to detect an event, so that results in attenuation. But it's also possible for you that because of scattering, you do detect an event, and that becomes a scattered event. So scattering, the phenomena of scattering can result in attenuation, meaning something that was intended to be detected was not detected because of scattering. But it's the other way around too. An event that was, for example, not meant to be detected, it might be scattered and then be detected. And in fact, in PET, you could have an event that was even meant to be detected, and it was scattered, and still, again, it was detected. So scattering can be confusing, but just hang in there. And the collimator blurring is this phenomenon we've mentioned. As you get away from the detector, from the collimator, the resolution degrades. So in chapter 6 of our text, and Carlos talked about different interactions, but in chapter 6, we have this kind of a nice diagram where it talks about the relative contributions of photoelectric effect and Compton effect, okay? And pair production is not really a concern. Pair production, Carlos talked about, that only happens when you have your energy, gamma ray energy is more than 2 times 511 kV, more than 1,000, 22, right? But in nuclear medicine imaging, that's not really something we encounter in typical nuclear medicine imaging. We're far below that. But look at the relative contributions. And just going back, because we had a question, collimator blaring, just hang in there. We will we will come back to this and explain this more. But the idea is, if you're here versus if you're here, okay, so let me put it this way. It's what we've said before. As you get away from the collimator head, from the collimator, the resolution degrades. So if an event is here, if an event is here or here or here or here or here, all of these could be detected here. Whereas here, a narrower range could be detected here. So basically, this results in, because you don't know whether this event that you detected here came from here or here or here or here. So you have some kind of a resolution degradation. So you're kind of having this distance-dependent resolution problem that you have to tackle. And we're going to have some slides about that. Back to here. Within the body, you don't have to worry about, lead and sodium iodide, but within the body, let's say look at water or bone. At around 100 kV, or let's say 140 kV, in the bone, you could be having some contribution from the photoelectric effect, but primarily it starts to become more and more Compton. At 511 kV, which is what we have in PET, you don't even have any photoelectric contribution anymore. It's all Compton scattering. But the point I'm just trying to make is, an event that is supposed to go and be detected could be not detected, which means it could be attenuated. So you're detecting less events, either because it was absorbed due to the photoelectric effect in the body, or it underwent Compton scattering and it just changed its direction and therefore was not detected in that collimator. Okay? So both of these phenomena can contribute to attenuation. But in PET imaging, where you're at 511 kV up here, you don't really have contribution from the photoelectric effect. You only have contribution from Compton scattering. Okay, so attenuation in SPECT is significant. The average attenuation factor, for example, at 140 kV could be around, let's say, 2, 3. This could increase up to, a factor of 5 in the abdomen, right? So factor of 5. That is significant. It's almost like the counts you're measuring has been lowered by a factor of 5. It's a significant drop, right? So obviously that gives you more noise, right? Because you're detecting less events, but also it has a quantitation problem, because along certain pathways you're attenuated more, along certain pathways you're attenuated less, so your image may not be quantitative anymore. So SPECT reconstruction using filter back projection sort of ignores the effect of attenuation. You could come up with fancy ways of dealing with it, but it's really in statistical iterative reconstruction that this problem has been really properly addressed. So you could do some kind of corrections, but we're going to show you some examples of ways people have done corrections. They've been typically, very commonly, approximation methods. They have not been ideal. But in statistical iterative reconstruction, it's been done really well. But let's just take you through some of that history. So the consequence of attenuation is that there are less photons detected from deeper structures in the body than from tissues near the body's surface. And reconstruction, for example, of a uniform source will demonstrate that counts are low towards the center. Because if you have a source coming from here, going in all directions, it will be attenuated. So the center, you're going to be losing a lot more counts from something coming from the center than something from the edge. Because if this thing is at the edge, for example, going this way or going that way, it's not losing anything due to attenuation, right? So So you're definitely getting more attenuation in deeper structures. So if you image and don't do any attenuation correction, you may get this dip that is commonly seen, right? And in the past, clinicians have gotten used to these ideas, and so they adjust their reading, their mindset to sort of correct for this. But the thinking is our job as physicists and as engineers is to design systems that give you more reliable numbers, so you don't have to do that mental adjustment in your mind. Okay, so here's what we have, and unfortunately, the body does not have a uniform attenuation in most areas, and so this makes it even more complicated. So you get this problem even in a uniform, structure, but it will be even more complicated when you're going through the lungs, through the bones, and through all kinds of different tissues. So you have to deal with this. So again, however, for brain and let's say lower abdomen, you could sort of assume that there's uniform attenuation. And so this leads to the so-called Chang method. If you can assume, let's say in the brain, that you have uniform attenuation, that the tissue is pretty consistent, then you could do some kind of correction methods that are not bad at all. So here's an example of the famous Chang's method that used to be used a lot or significantly. It is very feasible because it's purely software-based, no special equipment, so you don't add any transmission source or CT needed. So this has been kind of popular, somewhat popular in the past. The method is, however, an approximation, and it calculates the average attenuation for photons traveling from each point in the body at different angles. And then it multiplies each pixel value in the image by a correction factor. So let's try to understand this. How does this work? First, you reconstruct an uncorrected image. There's no attenuation correction. You get an image like this, okay? Then you use this image to estimate a boundary. So based on this image, because you don't have a CT scan, right? Based on this image, you kind of guess where are the edges of the brain. You sort of draw, let's say, some kind of an ellipse or whatever to sort of represent that. That you're going to say, okay, this is kind of the outline of the brain of this particular patient. And you kind of assume that now there is uniform attenuation within this structure, not uniform activity. Obviously, the radio tracer is distributing differently. That's what you want to reconstruct, but you assume that the tissue is the same everywhere. It's just soft, just soft tissue. You assume like it's water or soft tissue there. And then you assume, again, a constant attenuation coefficients everywhere, the mu, the attenuation coefficients everywhere. And you basically take each pixel and you draw all kinds of projections from it, and you calculate what is the attenuation probability or the probability of survival for it to go through all of these not being attenuated, and then you average those. And you take the inverse of those average numbers, and that becomes the attenuation correction factor. And then finally, you take your uncorrected reconstructed image and multiply by that. Okay, so let's look at some math here. So look at this expression here, e to the power of minus mu, okay, times di. You're assuming that, again, mu is constant everywhere, and di, for example, would be the path length here from this all the way to the edge of the brain, let's say. So you pretty much multiply the mu value, the attenuation coefficient, by this distance. You do e to the power of the minus, e to the minus mu times d. That is the probability of survival. That is the probability that an event originating from here will pass through here, not attenuated, right? And then you do this for all of these, and you average them. So that's the probability of survival that is not attenuated. And so that's going to be like the average probability that it won't be attenuated. And then you take the inverse of that because you want to multiply your images by that. So then you take your uncorrected image, which looks like this, and for each pixel for which you've done this calculation for all these path lengths going from it, you multiply it by this, and you end up getting something like this. Now, you might be asking, wait a minute. You are correcting for this. Now it's almost like the opposite. Now you have like a hump, right? And some people actually who would see this, they would be like, maybe attenuation correction is not exactly, some people would say, well, attenuation correction is not working. But actually, it turns out it is working. This hump here is because of scattering, which is a whole other phenomena. So it's almost like you correct for attenuation and then another problem shows itself. That doesn't mean you should not be doing attenuation correction. That means now you got to move to the next iteration and now correct for scatter. So just remember that point. So first you correct attenuation, then the new problem shows up, just like in life. When we solve one thing, the other thing shows up, and now we're going to tackle and address that. But so that was the idea. So let's ask you guys a question here. Let's poll you guys. So the question is, if for a pixel, the average probability of not being attenuated is 20%, how much is the attenuation correction factor? Think about it. If the average probability of you not being attenuated, meaning you surviving all those projections from your pixel to all those directions, is 20%, what number should we be multiplying the values in our reconstructed images by to get the correct number? What number should we be multiplying? Attenuation correction factor is a multiplication factor. What number should I be multiplying my reconstructed value in that particular pixel by to correct for it, to compensate for this effect? Yeah, so answers are coming in. And a hint here would be, as answers are coming in, a hint here is that number obviously actually has to be more than 1, because attenuation correction factor is a number you multiply by. That number has to be more than 1 because you're losing events to attenuation. So you should be boosting up the activity, multiplying it by a certain number. Okay, so yeah, so the correct answer is, let me activate my drawing capabilities here, is going to be, yeah, it's going to be 5, as most of you have said. So here we go. Okay, so, all right. So the reason is, yeah, so most of you selected C as is the correct answer. So the answer is 5. And again, going back to this formula, look here. We were saying that the average probability of survival of not being attenuated was 20%, meaning 0.2. So this number, this average, the probability of survival of not being attenuated is 0.2. So 1 over 0.2, that gives you a factor of 5. So the correct answer is C, 5. Okay, so again, showing you the fact that if you're doing no correction, you get this sort of a dip, right? And then when you do attenuation correction, then suddenly this weirdness appears, and sometimes it may be almost a hurdle. You're like, wow, I tried to correct this, but it didn't work out, but it did work out. You got rid of the attenuation problem. Now you have another problem, that is scattering, because attenuation is a loss of events, especially from deeper structures. And now that you've corrected it, turns out that now scattering, because you have a higher chance of also scattering from deeper structures, you actually are getting now a contribution from here. So you get this. So then if you do scatter correction, and we will talk about that next, then you start looking like an image like this, which looks flat as it should be, and that is nice. And then on top of that, you could do so-called resolution recovery, and that is to deal with, you know, those problems of resolution degrading, for example, as you move away from the collimator blurring or detector collimator blurring. So you can sort of keep getting better and better images, etc. So again, to sort of summarize the essence of Chang, which is not being used much anymore, thankfully, because we're doing better things. The problem with Chang attenuation correction is that use of a constant attenuation coefficient is inappropriate if the attenuation is non-uniform in the body. For example, in the chest, where attenuation in lungs is approximately a third of the attenuation in other tissues, or for example, when you have bone, where the attenuation is more, right? However, it has been traditionally popular and commonly available on commercial SPECT systems. And again, that's because it was purely software-based. It was easy to do. And again, it does work reasonably in like areas where uniform attenuation assumption is reasonable, like in the head and lower abdomen, but not good in like along the chest or the pelvis and things like that. Now, but let's move to more realistic situations where you do try to deal with non-uniform attenuation. So to do that, the best approach is to actually measure the attenuation coefficients directly. Now, you could use this conventionally. People who did try to do that will use transmission sources, but even better and faster are to use CT systems. So like a combined SPECT CT. So here's an image of a combined SPECT CT as an example of a camera. And this is an example of anatofunctional imaging where the color bar is the SPECT, and you see this grayscale is the CT, and they're superimposed. It has clinical value, significant clinical value, but also the CT can be used to estimate the attenuation and actually do attenuation correction for SPECT. So the CT actually is starting to find, two major roles in SPECT CT and PET CT systems: to do attenuation correction for the SPECT or PET, and also to add value for clinical interpretation. SPECT CT offers an advantage of good quality or even diagnostic quality CT scans, which is the trend. So again, you're measuring attenuation maps and allowing fusion of SPECT or PET with CT, so you're doing anatofunctional imaging. Now, it turns out if you do that, then you could still do another kind of Chang correction. And that is by the following idea. So imagine that you have measured the mu maps at the different pixels, let's say using a CT scan. Okay, so now you don't assume that the mu's are uniform everywhere. You don't assume that. And we have a question here whether, about attenuation correction. Attenuation correction does not increase scatter. Attenuation correction allows you to see the effect of scatter. So before that happened, what was happening was that you had both attenuation and scattering, but attenuation effect is more dominant. So it was kind of hiding the effect of scatter. So when you got rid of the attenuation problem, when you corrected for attenuation, suddenly you started to see the effect of scatter. So it was being clouded, it was being covered up by attenuation. Once you correct for attenuation, then the effect of scatter showed itself. So back to this here. Okay, so you have these different mu maps, or they have a mu map with different mu values from the CT, not assuming it's uniform, and this is your original non-attenuation corrected image, and you want to multiply it by a correction factor. Well, yeah, so the point is now you could do the exact same thing you were doing before, but you just don't assume.
It's 10 o'clock.
Don't assume the mu maps are uniform. So then you get the correction factors that way. So just like here, we were assuming that the mu values were uniform everywhere. But now you don't assume that. You say, here, this becomes a summation itself, like a multiplication of two vectors where you have, this pixel length, length along this pixel multiplied by the mu value in that pixel, then this pixel, then this pixel, then this pixel. So you can actually build a non-uniform mu map in here, calculate the attenuation along here, given that non-uniform mu map, calculate this, and then do the attenuation correction. So pretty much all you've done is upgraded this model where you're not assuming the mu is constant everywhere. You're getting help from a transmission scan or from CT scan to understand the mu map. Okay, so back to here. So now you get these better correction factors, attenuation correction factors, ACFs or correction factors, and now you get an image that presumably looks better. Okay, so what we are having here are examples where especially before CT and SPECT were combined. And by the way, this happened sort of in the late 90s, where SPECT CT were combined, PET CT were combined, and then, but in the commercial world, PET CT scanners started to really quickly appear in the span of just 3 years, from year 2000 to year 2003. Almost all PET scanners became PET CT scanners, whereas SPECT CT has taken a longer time. We still have SPECT only cameras, but more and more we're having SPECT CT. But before CT was used, commonly, if people wanted to do proper attenuation correction for SPECT, they would be using transmission sources. So there's different ways of doing this. But essentially, the idea was that you had like a isotope, radioactive isotope, that would be sort of effective, kind of like doing a CT scan, but you would get lower resolution scans and it would take longer to do the imaging. So it's kind of almost like a lower quality CT scan. So you could be having, for example, these line sources or rod sources. This point represents not a point, but actually it's a rod or a line source. Just that from our view, it looks like a point, but this is actually a line source here. It's a line source like this, but it's moving this way. So you're scanning this. So you're sort of kind of in the same as a CT. You're kind of shining X-rays in the case of a CT, or gamma rays in this case. And it's going through the subject, and it is being imaged on the other end, and then you're rotating around the patient to do this at many different angles. Or you could do like flood sources. A flood source is like a plane. So this is actually it's a plane. It's just that from our view here, it's a line. It's actually a plane, like a flood source, like a 2D radioactive source that is just placed there, and it is doing this. So again, you could be doing that. You could be doing a moving rod source. You could be having like a dual head where you're having two line sources that are moving. Or in case of a triple head, you could be doing like, again, a rod source, a line source with like a converging collimator, et cetera, et cetera. And then you could be, for example, putting a different energy window. For example, if you were doing technetium 99M imaging, so you're having, this is a standard 140 keV emission window, but let's say you were using a source, let's say gadolinium 153, whose energy is around 100 keV. So now you would be placing an additional transmission window if you're doing simultaneous imaging. And that allows you to be doing your emission imaging, to be doing your transmission imaging. And then this transmission imaging gives you kind of like a low quality mu map, which is sufficient for our purposes. And then you would use that to do attenuation correction here. One of the problems with this approach is downscatter. So you could be having 140 keV events going here, but because they were scattered in the body, their energy would be lowered, let's say to 100 keV, and then they would be accepted by this window. So that would be a problem, right? Because what was accepted in this window was not the original, transmission source signal coming through, but it was actually an emission signal that was mistakenly thought to be a transmission source. So this kind of crossover or downscatter problems. And there are a different number of isotopes that have been used in the past that you can sort of see: gadolinium, tellurium, cobalt, and barium that have been used. And the half-lives tend to be very long, right? Because you don't want to be changing the source, every day. You want to change it after every, year or two or whatever, right? So you don't want to change it every day. So that's what you have, and you can sort of see the different energies that were. And these are the kind of images that you may get. There's a transmission image, which again looks like a low quality CT image, and it's fine. It's fine for transmission correction. The problem is, these downscattering problems. In the world of PET, you don't even have, in the world of PET, again, this is also the same thing. So people would do transmission at a different time than the emission. Okay, for example, right? So to minimize these complications, overlaps, but that adds time. And these scans, for example, would take, let's say, 6 minutes for a single bed position. If you want the whole body, it's going to take like half an hour. And if you're adding half an hour just to do something that using a CT scan, you could do in a few seconds. So that's why, you know, this transmissions approach has really been replaced by the state-of-the-art, you know, CT framework of thinking. Okay, so imagine you're doing imaging without anything in between the source and the detectors, kind of like a blank scan, reference scan without the patient. And then when the patient is in there, you get this. So without the patient, you get this. With the patient, you get this. So here, this is the attenuation formula, where, as we said, mu here does not have to be assumed to be uniform. So this mu is actually a vector. So when we say mu times x, we mean like a vector multiplication. So you're doing mu of each pixel. Here I represents pixel number, okay? And so you kind of have this formula. This is a standard formalism for a CT image reconstruction, that you measure, so that you measure what was transmitted, and based on that, you reconstruct the mu map. So you do the same thing here. You reconstruct the mu map, the attenuation map. So that requires you to do a scan without the patient. So that would be done, for example, once a day in the morning, just one scan in the morning. And then for every, like a blank scan, and then with every patient, you would do this, and you would be doing these computations. So if you have estimated the attenuation map, then you can do the Chang method. Okay, so obviously it's a better method than assuming constant mu values. We've said that multiple times. However, the issue is that the original reconstructed image without, you know, attenuation correction, without mu value, without attenuation correction itself may have been really fundamentally flawed. You were assuming no attenuation. You reconstructed an image. Of course, you want to multiply it by Chang, but that original image you reconstructed might have been from very inconsistent projections. So the reconstruction is flawed. So this is an approximate method, even if you end up multiplying it by some factor that assumes the correct mu values. The reconstruction to start with is flawed. So to deal with this, people have come up with things like the iterative Chang method, where they say, okay, once we're going to do it, then we're going to go back and we're going to say, okay, now we have a new updated image, but let's use this new updated image to calculate, you know, things. And let's just keep iterating and iterating until the image that we have, when forward projected, assuming all kinds of correct attenuation, matches, you know, the kind of data we're getting. Now, the spirit here is actually quite similar to iterative reconstruction. But as I said before in a previous lecture, when we say iterative, we really mean statistical these days. You could have iterative non-statistical methods, but nowadays, statistical methods that model the Poisson nature of noise, for example, have become so popular and so effective that we call, when we say iterative by default, we mean those. And the beauty of iterative and statistical reconstruction is that you have this so-called system matrix formulation, where within it you could really place attenuation very, very naturally. And on top of that, you're modeling the Poisson nature of noise. So it just makes a lot of sense to do this comprehensive, proper modeling instead of like doing a recon without attenuation correction, then looking up for some multiplication factors. Why can't we just model the physics properly in the original reconstruction problem instead of doing it in multiple steps? And that's what's really worked nicely. So again, the formulation is like this, where this is the object that you're having. This is a so-called system matrix that models the physics of how you go from an object space, from the image space, the object space, to the projection space, to the data that you measure, and then there's some noise, which is typically modeled as Poisson. The iterative reconstruction framework and the statistical iterative recon framework deals with this problem very, very effectively. It models the noise properly. It can incorporate the physics by more comprehensively modeling system matrix. In a future lecture, we'll talk about the specific algorithm implementations mathematically. We had a prior lecture about just general frameworks, but not much math. In the future, we will have more math. But the point is, this so-called system matrix can model these different phenomena. You can actually model the attenuation in here. You could model detector blaring in here, for example, right? So why not just model things properly, and then you're modeling the noise too in statistical framework, and then do the reconstruction of X properly. And that's what's really worked out very, very nicely. So just to summarize, attenuation correction methods have been as follows: doing nothing, and just having the physician and the radiologist adjust their thinking as they look at artifacts and things like that. Doing Chang, either using assuming uniform mu values, or better, assuming non-uniform mu values as estimated using transmission scans or CT scans, or stepping it up a notch and doing iterative Chang to improve this method, but really doing comprehensive statistical iterative reconstruction when everything is properly modeled is the best approach, and that is really what's made a tremendous difference, at least with regards to doing nothing, right? These two methods might, I mentioned the paper here. You could refer to here some interesting frameworks of doing iterative Chang, but at the end of the day, this is more statistically sound, and that it makes a lot of sense to do this kind of modeling. So here are examples where you have rest and stress cardiac, no correction. These are the kind of images you might get. When you do attenuation correction, these are the kind of images that you get. So the clinician doesn't have to adjust their thinking, saying, oh, this is an attenuation artifact, not a real artifact, And they have been trained to read that way, but hopefully with newer generation scanners, they don't have to even be trained to really correct in their mind for these things, and the images would be tackling these properly. Image reconstruction will be tackling these properly. So here are some questions for you guys to try to attempt to answer. So scatter correction, let's talk about that. Scatter events are a challenging problem for SPECT, typically about 20 to 40%, depending on activity and thickness. And a first attempt at scatter correction, believe it or not, has been to change the mu value that we use. So remember how I told you that, okay, use the Chang method, you assume a certain mu value, the true mu value, let's say for water or for soft tissue, but you get this bump. Well, they said, wait a minute, if we get this bump, how about we lower this number? Because we're kind of saying, this is overcorrecting, so let's lower this number to, let's say, to this number, and you're gonna get something like this. Okay, so this is actually something that was done. And some people call this broad beam correction. And it's because you think about it differently. It's like this. If you have a narrow beam that's going through here, all you worry about is attenuation along this path. But if you're having a broad beam, meaning that the beam could be coming from different angles, and it could be scattered from here to return back here. So some of the events that go here are scattered and then they're detected here. It's almost like you're getting more events because you're accepting from a broader beam. So the effective mu map, the argument goes, is therefore the effective attenuation is less here than here, because scattering is returning some of the counts to you. It's a sort of an argument like that. It is an approximate argument. It is not an ideal approach. So people have really tried to move beyond that kind of a mindset. And one really popular approach has been to be putting different scattering windows. For example, you could be putting just one scatter window below the photopeak window, estimate the scatter here, and then extrapolate to here. Or you could be placing two windows, one below, one above. So they actually call this a triple energy window, because there's three windows. There is a main photopeak window and two other windows below and above. And from these, you estimate the scatter here, you estimate the scatter here, and then you say, well, the scatter in this intermediate energy window would be sort of like an average of these two, and you sort of do that. But there are more elaborate computational methods that really go back to the physics. And for example, there's a so-called Klein-Nishina formula. You guys should definitely check out what the Klein-Nishina formula is. It's about cross sections and with, for example, for Compton scattering and for other energies too. But our key interest is for scattering here. And based on this formula, you can actually, if you have an initial estimate of what the activity distribution is, let's say you do a reconstruction with no scatter correction. You get some kind of a activity distribution. Based on that, use the Klein-Nishina formula to calculate how much scattering am I going to get in our projections. You take those projections, calculate your estimated scattering, and then you subtract those from the data, and then you do another reconstruction. So you could kind of iterate, kind of like the Chang method, where you first did reconstruction without any attenuation correction, then you estimated the attenuation, then again you applied some correction. Here too, you can first do a reconstruction without scatter correction, then use a Klein-Nishina to estimate how much scattering there is, and then you could subtract that estimated scattering amount from the projection data, and then do another reconstruction, kind of like that. But it's quite advanced, and you guys feel free to investigate this more. But it's not something, perhaps even for your term paper, somebody can investigate this more. As a sort of a summary, there are 5 different ways, for example, that I mentioned here to do scatter correction. There's Monte Carlo-based scatter calculation, which is very, very time-consuming. You could do Klein-Nishina type of formulas, which is definitely less time-consuming, but still somewhat time-consuming. You could do Monte Carlo, but in pre-calculation. So you have like some simplistic like geometries, and you pre-compute how much scattering you get, and you get some kind of kernels that have been arrived at using extensive Monte Carlo simulations, but you only have to do them once, or for just simple geometries. They're pre-computed, so then you could apply it. I talked about the double or triple energy window method, and also the sort of, I would say the least ideal one is the broad beam Chang method. And here are some questions. And because we're in the interest of time, we're just going to wrap up here. I already showed you this figure. All I want to add here is that on top of all these corrections, on top of coming close to the patient, all these things, you can model resolution within the iterative reconstruction. We call that resolution recovery, or also collimator detector response compensation. Kind of looks like this. Instead of just sort of doing your projections like this, you would be really modeling the fact that as you get away from the collimator, you're having a wider acceptance angle. And so instead of doing like a line integral or a strip area in a model, you sort of start to do your projections more properly using the proper cone geometry that models this effect. So if you do just a conventional, let's say these are 6 spheres reconstructed, but as you do better and better modeling, so these are statistical iterative algorithm that we talked about for order subset expectation maximization. You could do this only in the 2D, but why model the resolution degradation only in 2D? It's both ways, this way and that way. So that's what we call 3D modeling of that phenomena. So not just modeling in this direction, but also modeling axially, for example. Then you get better and better images. And so this is my concluding slide. SPECT was considered for a long time not to be quantitative. The increasing usage of statistical iterative recon with improved modeling of attenuation and scattered has made SPECT much more quantitative. Iterative recon methods can also model the collimator detector blaring effects, so-called resolution blaring, that leads to so-called resolution recovery methods or resolution modeling methods. We're going to talk about this later, especially for PET or detector collimator blaring compensation, different names for the same thing. And so again, you've moved from an image filter back projection type of reconstruction with no correction to images that look quite better. So here's an example where you do filter back projection, but with Chang attenuation correction. Here you switch to statistical iterative recon with no correction, with attenuation correction, with resolution recovery, and also with scatter correction. And you sort of see the trend. So images have become definitely more quantitative, and different vendors use different compensation methods. For example, for scatter correction, I have a sense that even triple energy window is very popular for scatter correction, but people are moving to other methods. In PET imaging, Klein-Nishina is popular. I have a sense that as SPECT images become better and better and better, people are going to use better and better and better scatter correction methods, like that we mentioned here, for example. Moving towards Klein-Nishina formula, even possibly Monte Carlo methods if they can do it super fast. And so people are thinking about this, people are trying these ideas. So that's it. So if next time somebody tells you SPECT is not quantitative, you can say, maybe not on your scanner, but it can become quantitative. And hopefully we will all be moving towards an area where SPECT is being done routinely in a quantitative manner. So thank you very much.